In this video, we're going to look at how you can assess parametric assumptions for a paired samples t-test. So we're going to base it on a study performed by Mir et al. And they was interested in whether melody can communicate social information in children. So they had a within subjects or paired samples design where they measured a child's proportion gaze to a singer who sang the familiar song and a singer who sang an unfamiliar song at baseline. They then measured it again after the singers had sang their songs. And they was interested in whether the proportion of the child's gaze would increase towards the singer of a familiar song from the first time they measure to the second time they measure. So we've got two columns we're going to look at. And there are two key things we want to look at in a paired samples t-test. We don't want them to be any influential outliers. And we also want the residuals of the model to be approximately normally distributed. So the first thing we're going to explore is whether there are any influential outliers. So one of the first ways to do this is to explore what the data looks like. So we want to visualize the data. And one of the easiest ways to doing this is to create what's called a box plot. So if we go Analyze, Descriptive Statistics, and Explore, we have a box for the dependent list, a box for the factor list. So in a within subjects design, we have two columns of data. So we want both of those columns in the dependent list. So if we drag baseline proportion gaze in the dependent list, test proportion to gaze in the dependent list, at this point we only want plots. So if we select display plots and go into the plots options, if we kept it as is, you'd get one box plot for the first variable, one box plot for the second variable, but we can get a little bit more information. So we want to compare them side by side to make it a little bit easier. So if you click dependents together, rather than split them into separate plots, it will show both variables next to each other. We don't want a stem and leaf diagram. But we do want normality plots with tests. So we'll come back to this later on, but we'll have it in the output for now. If we click OK, we should then get some output. So if we scroll down to the bottom, we have two box plots side by side. So the first one is the baseline proportion gaze to singer. So here we can see the box plot is roughly symmetrical. So we have the center line being the median, the bottom and top of the box being the 25th and 75th percentile of values, and the two lines extending out are the plus or minus 1.5 times the interquartile range. So one of the informative features about this in SPSS is it will label any potential outliers for you. So if there are any values outside of these lines, it will indicate them with a little circle. So we can't see any here, so it doesn't look like there's any influential outliers. But if there were to be, if there's any beyond the lines, it will be indicated as a little circle. And if there are any extreme outliers, so this is what SPSS classes as 3 times the interquartile range, it will be indicated as a star. So that's to show it's an extreme outlier. So although we can be pretty confident that there aren't any influential outliers present here, there's a second way we can look at these values, and it takes a little bit of processing. So if we go back to the data file, one of the other ways we can look at outliers is to convert the values we're interested in into what are called standardized values, or z-scores. So this is where you convert the values to have properties of a mean of 0 and a standard deviation of 1, and it's expressing the values in standardized units. So the first thing we need to do is create two new variables for the z-scores. So SPSS handily does this. So if you go analyze descriptive statistics and descriptives, so I'd already dragged these across, but if you'd already had them on the left, if you drag both baseline and test into the variables box, tick save standardized values as variables, and click OK. And although we'll get a little bit of output for the descriptives, we don't need that at the moment. If we go back to our data file, we now have two additional columns at the end of our data file. And the values look a little bit different because this is they're expressed in standardized values. So both of our variables have been transformed to z-scores, which you can see by SPSS will give it a name of the original variable name with a little z in front of it. And to make it a little bit easier, we want to do one more thing. We need to create another column by converting into what's called the absolute value. So this is going to make the next step a little bit easier. But this time we want to compute a variable. We're going to have to repeat this twice. So if we start from scratch, we need to give the target variable a name. So we can have z baseline absolute. And when you first start, this will be on function all. We need to go into arithmetic and ABS, the very top one. So if we double click on this, it will auto-complete it in the numeric expression. And what ABS does is it will calculate the absolute value of a variable. And what this means is it will take away the plus or minus sign, so all of the values will be plus. So this will make the next step a little bit easier. So if we do this, so we want the z-score for baseline. If we double click on that when the the false question mark is highlighted, so we've got ABS brackets z baseline proportion gaze. If we click OK, it will tell us that it's been computed in the output. If we go back, we want the second variable. So if we go compute again, and it will already have this information there, but we want to change it slightly. So instead of baseline, we now want test. So we've got z test absolute. We can keep the ABS and brackets part, but now we want the z-score for the test proportion. So if we double click that, we should now have ABS bracket, Z test proportion gaze to Singer, close bracket. If we click OK once again, that will put in the output. And we now have got two more columns. So what you will see is if you compare the values from the original z-scores to the absolute values, they should all be exactly the same, but the plus or minus has been taken away. So they will all be positive values. So what we can do now is when you convert to z-scores, it has some helpful properties. So most of the values should be between 0 and 1.96. So because we've converted this to absolute values, normally we'd be looking at minus to plus 1.96 because it would be a two-tailed distribution. But because we've converted it to positive values, we're going to look at the same number, but we're expecting slightly different percentages. So once we have these, we can get SPSS to recode the values, because what we want is we don't want any more than 5% of the values to be bigger than 1.96. So we'd want 5% roughly to be bigger than 1.96. We want at the most 1% to be bigger than 2.58. So remember, this is in z-scores, so in standardized units. And we don't want any values to be bigger than 3.29. So we can get SPSS to calculate this for us. So what we can do, we can recode this into a different variable. So what we need to do is start with the absolute value that we've calculated. So we've got z baseline absolute for a starting point. If we drag that over, we need to give it a name. So this is going to be another column we're creating. So at this point we can have baseline outliers, click change. So we're going to be creating a new column called baseline outliers, and it's going to be based on recoding the values from the absolute z-scores. So if you click old and new values here, what we need to do is give it a range of values and recode them. So anything bigger than 3.29, we're going to call a 1. Anything bigger than 2.58, we're going to give it a 2, and so on to cover all the values we've talked about. So we're going to start with range through highest, and what this means is if we put a value here, it will go from the value you state up until the highest value in the data set. So if we start with 3.29 through highest and give that a 1, what it will do is in the data set, if there are any values between 3.29 and the maximum number within the data, it will label it as a 1. We can then redo this because it does it in stages. So we can go range value through highest 2.58 with a value of 2 and add that. One more time for this, we can do 1.96 and we can give that a 3. And then this time we want the range lowest through value of 1.95. So what that will do is it will the minimum value in the data set up until 1.95 we'll then give that a value of 4. So you can see that with the different numbers we will expect, so the boundaries that we're looking at, we give it a different value. So if we click continue and OK, SPSS will tell us that it is calculating that. So what you can see is we've got lots of 4s, a 3 in there. To make it a little bit easier to look at, we can put a value and label on this. So if we go to our baseline outliers, so for any value we gave a 1, that was an extreme outlier. Any value we gave a 2 was a probable outlier. 3 are potential outliers, so anything bigger than a z-score of 1.96. And 4, totally normal. So values that we are perfectly fine accepting. So we've got 1, 2, 3, and 4. If we click OK, we can then go back to our data view, and we can see that in this data set, everything looks pretty good. We've got totally normal for everyone but one potential one. But if we remember back, we can expect about 5% of those to be greater than 1.96, which is this potential outlier. So because we've only got 1, it's perfectly fine to deal with. So there's no outlier we can be really worried about in the baseline. And we can repeat this process for the second one. So for the test, so if you want to do that in your data set, you can. We won't repeat the process now because there is only one more in the same participant. There was a potential outlier in that one too. The rest of them was the same. So we've shown 2 different processes you can use to identify outliers. You can either look at box plots, and SPSS will label them for you, and then you can look at your standardized values to see if you have any z-scores above these ranges that we've highlighted. The second thing we want in a paired samples t-test is we want the residuals to be approximately normally distributed. So this means that the difference between values you observe in your data and the values you would expect in the model, if it was a normal distribution, are normally distributed. So if we go to descriptive statistics again and explore, right, go back one step. So we need to compute another variable. So we can get rid of these. So under the hood, when you calculate a paired samples t-test, it looks at the difference score, so the difference between condition 1 and condition 2. So instead of looking at both conditions, we can calculate a difference score and see whether the residuals of that are normally distributed. So if we go gaze difference, we want to know if the difference between baseline and test is normally distributed. So if we go baseline and then a minus sign, and then we put the test proportion in, if we click OK, so remember we've called it gaze difference, if we go back, we'll have a final variable entered into here. So this is the difference in our gaze proportion between the first condition and the second condition. So now we go analyze descriptive statistics and explore. So we don't need these anymore. But now we need the gaze difference, which will be the bottom one. And if we enter this into the dependent list, we can keep the settings as before. The dependents together doesn't really matter because we only have one variable now, but this time we do need the normality plots with tests. So we're going to actually use this information now. If we click OK, there are now two things we can look at to assess whether the data meet the assumption of normality. So the first is what's called a normality test. So there are some statisticians who would argue that this isn't a very effective way of assessing normality. So it's based on a significance test itself, so it calculates a p-value. And if we have fewer than 50 participants, we want to look at the Shapiro-Wilk test. So what this does is kind of flips a normal t-test on its head. So instead of comparing the results that you observe to what you would expect under the null hypothesis, so a mean difference of 0, here the null hypothesis is the data are normally distributed. So what it does behind the scenes is it will compare your results or the distribution of your results to what you would expect under the null hypothesis, which is that the data are perfectly normally distributed. So following the logic of hypothesis tests is if there is a very small p-value, it would mean that if you was to assume the null is true, in this case that the data are normally distributed, your data would be surprising. So it would be unlikely. So given that we normally look for a p-value of less than 0.05, this would mean that we would reject the null hypothesis and reject the fact that the data are normally distributed. So you're looking for the opposite here, where a significant result would mean that the data are not normally distributed, or at least sufficiently non-normal to give you something to worry about. But because it's based on p-values, it has similar kinds of limitations to normal t-tests as well. So if you have a very big sample size, it can be very sensitive. So it will produce a significant result even when there are very minor differences between what you would expect under the null and your observed results. And likewise, if you have a very small sample size, it can lack statistical power. So even if you have large deviations from normality, it will show as non-significant. With that in mind, what we have here for this example is a p-value of 0.745. So following the traditional threshold of 0.05, it would suggest that the data are at least approximately normally distributed, so following the logic of this test. But because it's not the best method to assess for normality, we can look at a second thing called a QQ plot. So what this does is it will directly visualize the residuals. So on the x-axis along the bottom, we have the observed values. So the actual values that we have in the data set, so our sample values. And on the y-axis, we have values we would expect if the data were perfectly normally distributed. So if the residuals are normally distributed, all these dots will fall roughly along the line. So we can see that there's some jiggle around, but they follow the line very closely. We've got one value at the bottom here between sort of -2 on the y-axis and about minus 0.55 on the x-axis. That one's a little bit further away from the line, but it doesn't look like it's too different. And given the fact we've already looked at outliers and there doesn't seem to be anything seriously wrong with being influential outliers, we can be pretty confident this isn't causing too much influence. So almost all of the dots are just nicely nestled around the line. So with both of these pieces of information, a non-significant Shapiro-Wilk test, a QQ plot that looks okay, we can be pretty confident with going forward with the parametric test. So at this point, you could look at calculating the paired samples t-test to compare the difference between the baseline condition and the test condition.